Hey everybody, I hope you've had a great week. Today we're going to be going over some Chapter 16 example problems and looking at linear equations and regression. Our first problem provides us with a raw data table, and we are asked to find the regression equation for predicting y from x. The first element that we'll need to find our regression equation is the sum of x. We'll take all of our scores in our x column and add them up and find the sum of x. Next, we'll find the sum of y by doing the same thing, adding all of our y scores up and come up with the sum of y. And then we'll divide each sum with the number of scores to find the respective means for x and y. And then we'll multiply each x by its corresponding y value to determine the sum of xy. Next, we'll calculate the sum of x squared by taking each x score and squaring it and adding them together. Next, we'll find the sum of products by taking the sum of xy and subtracting the sum of x times the sum of y divided by the number of scores. The next equation that we need to determine our slope is the sum of squares for the x scores. We'll take our sum of x squared and subtract the sum of x squared divided by n. To calculate our slope, we'll take the sum of products and divide it by the sum of squares for the x scores. To find our value for a, we'll take our mean for y and subtract the product of b times the mean of x. And in this case, we come up with a value of -1. In our regression equation for y hat is equal to b times x plus a, which is the y-intercept. Next, we'll plug our existing x values into this equation to determine y hat, or the predicted value of y, for each of our x values. Then we'll calculate the distance between the actual data point of y and the predicted point on the line, which is y hat, and square it. So in this case, our y value of 2 and the y hat expected value of 0.9 results in a difference of 1.1. And so when we square it, it equals 1.21. The sum of all of these values will give us our squared residual. Next, we'll find the sum of squares for y, which is the sum of y squared minus the sum of y squared divided by n. Now we can calculate our Pearson correlation for these data by taking the sum of products and dividing it by the square root of the sum of squares for x multiplied by the sum of squares for y. Next, we're asked to use our r squared value and plug it into the SS residual equation of 1 minus r squared times SSY to find SS residual. We'll find that we come up with the same value as we did earlier when we added up the difference between y and y hat squared. The next portion of this question asks us to calculate the F ratio to determine whether the regression equation accounts for a significant portion of the variance in the y scores. We already know our SS residual is 4.7, so we'll calculate our SS regression by taking our r squared value and multiplying it by the sum of squares for y. The sum of squares total is the sum of our predicted variability, which is SS regression, and our unpredicted variability, which is our SS residual. In a single regression equation, our total degrees of freedom will be our number of pairs minus 1, but the degrees of freedom residual, which will be the denominator for our F ratio, is n minus 2. The degrees of freedom of regression is the number of x, or predictor variables. In this case, we only have one. The mean square for both the regression and the residual are going to be the respective sum of squares divided by their degrees of freedom. Our F ratio formula is the mean square regression divided by the mean square residual, and equals 7.67. In order to determine the significance of our F ratio, we have to take a look and see what the critical region for F in this case is. So the numerator of our degrees of freedom will be our DF regression, and the denominator will be our degrees of freedom residual. We'll set our slider with an alpha level of 0.05 on the right, 95% on the left, and find our critical region is going to be beyond an F value of 12. If our F value is in the critical region, we would reject the null hypothesis and conclude that the regression equation does account for a significant portion of the variance for the y scores. Since our F ratio value is in the body and is not in the critical region, we will fail to reject the null and conclude that the regression equation does not account for a significant portion of the variance for the y scores. Our next example problem provides us with a data table that includes a number of churches, the number of serious crimes, and the population for a set of cities. We are told that there is a strong positive correlation between the number of churches and the number of serious crimes, but that could be because both the number of churches and the number of crimes can be expected to increase with population. We are asked to use multiple regression to evaluate the relationship between the churches and crime while controlling population. We'll start by finding the sum of the y values, and then the sum of the x1 values, and the sum of the x2 values, where the number of crimes is represented by the y column, the number of churches is the x1 column, and the population is x2. To find the sum of y squared, we'll square each value and add them together. We'll do the same for the sum of x1 as well as the sum of x2. So we'll square each value and add them together. Next, we'll find the mean of each column by taking the sum of that column and dividing it by the number of scores. In this example, we have 6 scores for each column, and so it'll be the sum of that column divided by 6. We'll need this value to determine the sum of squared deviations. To find the sum of squared deviations for y, we will take each score individually and subtract the mean. Then we'll square that value and add each of our squares up. We'll perform the same exact calculation for the x1 values, where we take our x1 values and we subtract the mean for that column, square it, and add them all together. Finally, we'll find our sum of squared deviations for x2 by taking the values in the x2 column, subtracting the mean, squaring it, and adding them together. As we continue filling out our chart, we come across the sum of x1, x2. We'll take each value from the x1 column and multiply it by the corresponding value from the x2 column and add all of these scores together. We'll do the same thing for the sum of x1y, taking each x1 score and multiplying it by its corresponding y value, as well as the sum of x2y. Now we'll find the sum of products of deviations for x1 and x2 by taking the values of x1 and subtracting the mean and multiplying it by the corresponding value of x2 with the mean subtracted from it. We'll do this with each of the corresponding pairs individually and add them all together. We'll perform the same calculation to find the sum of products of deviations for x1 and y, and then we'll find the sum of products of deviations for x2 and y. Next, we'll use these sum of squared deviations and sum of products of deviations to calculate our beta 1 and beta 2 values. To find the value for beta 1, we'll take the sum of products of deviations for x1 and y and multiply the sum of squared deviations for x2. Then we'll subtract the product of the sum of products of deviations for x1 and x2 multiplied by the sum of products of deviations for x2 and y. We'll divide all of that by the product of the sum of squared deviations for x1 multiplied by the sum of squared deviations for x2, subtracting the sum of products of deviations for x1 and x2 squared. It's easy to forget to square this value in this seemingly complex calculation. The beta 1 value is multiplied by x1 in the multiple regression equation. To find the beta 2 value, we will take the sum of products of deviations for x2 and y and multiply it by the sum of squared deviations for x1. Then we'll subtract the sum of products of deviations for x1 and x2 multiplied by the sum of products of deviations for x1 and y. Then we'll divide that by the sum of squared deviations for x1 multiplied by the sum of squared deviations for x2 and subtract the sum of product of deviations for x1 and x2 squared. The beta 2 value will be multiplied by x2 in the multiple regression equation. To find the value for the y-intercept, or a, we'll first take the mean of y and subtract the product of beta 1 times the mean of x1, and then we'll subtract the product of beta 2 times the mean of x2. And the value for a will be inserted into the y-intercept position of the multiple regression equation. The value of a capital R squared describes the proportion of the total variability of the y-scores that is accounted for by the regression equation and is calculated by multiplying beta 1 by the sum of products of x1 and y and adding the product of beta 2 multiplied by the sum of products of x2 and y. Then we'll divide the sum by the sum of squares for y. It's not likely that you'll get 1 for this formula, rather 0.999 or something like that, and so we'll be changing it later. We are then asked how much of the variance in the number of crimes does population size alone predict. So we'll start with the sum of products for x2 and y squared, because y is the number of crimes and x2 is the population. And then we'll divide that by the product of the sum of squares for y, which is crimes, and the sum of squares for x2, which is population. Next, we are asked to evaluate the F ratio to determine whether adding the number of churches as a second variable in the multiple regression equation added a significant amount to the prediction. In the multiple regression equation, our degrees of freedom residual will be n minus 3 instead of n minus 2. The SS additional that we are asked to calculate here is for the number of churches, which is x1. So we'll start with the regression for both x1 and x2 and subtract the regression with x2 alone. Then we'll multiply that by SSY to find our SS additional. For our SS residual, we'll take 1 and then subtract the percentage of variance accounted for with the multiple regression, so our capital R squared, and then multiply it by SSY. Our mean squares will be the sum of squares divided by degrees of freedom, and our F value will be our mean square additional divided by our mean square residual. In order to determine whether our F value is significant, we'll move our sliders for the numerator and denominator degrees of freedom, choose a one-tailed test, and move the slider to where there is 0.05 on one side and 0.95 on the other side. Since we see that we have a critical F value of over 10 and R value of 0.077 is way less than 10, it is not significant, and we will fail to reject our null. Well, I hope these problems have helped you with your Chapter 16 calculations, and I hope to see you next week. Take care.